you very much, and thank you for the opportunity to speak here. So indeed, I thought it was late in the afternoon, I'd do something light and speak about topological modular forms. I mean, that's the easy part. The hard part are the bilinear forms. Okay, so I mean, many of you might have heard about topological modular forms. Some of you certainly have not. And let me just give a very short picture what it is, and I will say something more later in the talk. So TMF is a certain E-infinity ring spectrum. And it comes, or more precisely, its homotopy groups come with a certain homomorphism. It's called phi to something I call MFT. These are integral modular forms of weight T. So if you don't know what it is, no problem, I will explain some more about this later. Okay, so this is why it's called topological modular forms, because there's this homomorphism. And actually, there's some things one can say about this homomorphism. First of all, phi is rationally an isomorphism. So it's pretty close, but phi is not injective and phi is not surjective. So not injective, well, so there's a lot of torsion in TMF, for example, eta in pi 1, and this is all mapped to 0 here. So in some sense, you can view TMF as something which is an amalgamation of modular forms and some part of the homotopy groups of the sphere. So we see a lot of the homotopy groups of spheres in TMF, but I see also a lot of modular forms in there. And it's also not surjective. For example, there is a certain modular form, delta, of weight 12, which is not in the image. So this TMF was put forward by Gauss, Hopkins, and Miller. They defined it a while ago. Nobody really knows when, because they didn't really write down their construction. But I guess about 25 years ago. And it has been used for a lot of stuff, like, for example, it figures when you want to compute the homotopy groups of spheres, it's good to know something about TMF. So one source on this, there's this book by Bob Brunner and Jan Rognes, where they use some stuff about atom spectral sequence of TMF to understand the atom spectral sequence of the sphere. And also, it figures a lot with chromatic homotopy theory. Wessner already mentioned that if you K2 localize, becomes some homotopy fixed points of some over E theory, so it plays also a role there. And actually, like, there's all this stuff about V2 self maps and so on, which is based on TMF. But today I don't really want to talk about chromatic homotopy theory. I want to start with a question which is more along these lines. Because when we say it's not surjective, we might ask, okay, what is the image? Actually known. And we might ask, so if you have some naturally occurring modular forms, you can ask whether they're in the image. And let me phrase a question along these lines. Theta functions in the image of phi. And again, I will say something more about what theta functions are in a few minutes. So, while I was stating the question here, it's not really the purpose of, not really what I want to do in these two talks to answer this directly for three reasons. First of all, this already has been answered by the man himself, Mike Hopkins. Some things based on work with orchards. The answer is yes. Okay. That's the first reason. Second reason is there's a slightly different question actually I want to address, which in some sense is more natural, I will come to later. The third one is actually like also there's still work in progress, so there are some things where we don't really have the complete answer. So in some sense, I will completely fail to say anything new about this, but still it will give me some excuse to talk about some things I want to talk about. And this is, if somebody tells you you have 2 talks, this is the main thing you want to do. Talk about some things you want to talk about. So, let me start to give a bit more background. What modular forms are, what topological modular forms are, also some non-chromatic homotopy theory reasons why they're important, and then come back to some parts of these questions. And I fear equivariant stuff will only enter next time, really, when I start more seriously to address this question. Okay. So let's talk a bit about modular forms. And now something happened which you maybe have not been expecting. Go to a conference on homotopy theory. There will be holomorphic functions. So a modular form of weight k is a holomorphic function. From the upper half plane to the complex numbers called f with 2 conditions such that f a tau plus b divided by c tau plus d equals c tau to the k of tau for all a, b, c, d, and SL2Z, and plus 1 extra condition I will hide. So that's what the modular form is. Before I come to examples, I also want to explain what this integral means in one way. So from this transformation behavior, you can see one thing pretty easily, namely you can look at the matrix. This one's clearly in SL2Z, and you will see that modular forms are 1 periodic, and this means there's something called a Fourier expansion, which says that f tau equals, where I set q to the 2 pi I tau. We can write it like this. And this is called the q expansion, for obvious reasons. And the first definition I want to give of an integral modular form is a modular form such that all an are in Z. So, in some sense, if you're like me, this is a bit of an evil definition because I have a limited tolerance for analysis, I have a limited tolerance for formulas. Not 0, but limited. So we want to translate this in a few minutes into some other more geometric language, but it's actually necessary also to go through this because this allows you to tell you what theta functions are. So let me give 2 examples, the theta function one in detail and mention also another one later. I hope I don't forget. So let q from z to the d to z be a quadratic form. And let b bw q b plus w minus q b minus q of w be the associate bilinear form. So actually you can take it as a definition of quadratic form that this associated cause effect is a bilinear form. And so then we can just define the theta function, q, to be the sum of all v and z to the d of q to the q of v. Okay? Or if you want to reorder this, you can also write it as n bigger or equal to 0. And then you have here q to the n, and here you have the number of v, such that q of v equals n. Okay. So these theta functions are extremely important in number theory. For example, these numbers, say you have some quadratic form, you ask yourself, how often does it attain a certain value n? It's a classic question. Number theory, like for example, your quadratic form might be in 4 variables, d might be 4, then might be the sum of 4 squares. And you might want to show that this number is always non-zero, which is known as the Lagrange 4 square theorem. And you can actually show this using modular forms, the theta functions. The modular forms are useful for a lot of things. For example, this dude hanging at the back proved Fermat's last theorem. Actually announcing it, I guess, at Newton Institute like 32 years ago. Theta functions are pretty useful. And I must say there's one condition, so that they actually are modular forms. We want that, so it's a modular form of weight d half if B is unimodular. Modular and positive definite. Okay, and so this one example, and I also want to mention again this second example. Oh, I didn't introduce this notation. Integral modular forms. So I use this notation MFD for integral modular forms of weight d. And then I have delta of weight 12, and one important thing is that I also have delta inverse. Modular form of weight minus 12. So this introduces this modular forms I already mentioned. So before we go on to, so first of all, any questions about this? So before we go on to TMF, I want to make a short geometric reformulation of this modular form thing, because this will make it much more transparent how to define TMF. So geometric reformulation. So just suppose now that k is 0, right? So if k is 0, these are just functions which are invariant under this action. Oh, there's the equivariance, we have a group action. So as to z acts on the upper half plane by this thing, k0 is just functions which are invariant. So, so if k is 0, the weight, then modular forms of weight 0 are functions on this quotient of the upper half plane by S to Z. So in general, modular forms of weight k are sections of a line bundle. On this guy. And to be completely honest, I should not just take a usual set theoretic quotient, but like a stack or orbifold quotient. And this line bundle is usually called omega to the k. It's not very hard to define. Define essentially using this action. It's trivial on H, and then on the stack quotient, you get a line bundle by using this kind of form. Okay, that's good. Actually, this guy also has a different name. It's called the complexified. Moduli stack of elliptic curves. So why is this? It turns out, so over the complex numbers, elliptic curve is just it's a torus with a complex structure and a chosen point. And it turns out that these points here are in bijection with isomorphism classes of elliptic curves. So meaning complex tori. And what can I do? Well, if I have some tor in the upper half plane, I take the quotient of C by the lattice, which is generated by 1 and tor. It's some copy of Z squared sitting in the complex numbers. So I take the quotient, I take a torus, which has a certain complex structure. And the point, well, it's the 0 point. This is a bijection, and you can make this point stronger to see that this actually, like this stack, is actually like in some sense a moduli stack of elliptic curves, whatever this exactly means. Okay. And then there's a theorem, which is a bit harder, which says that actually sometimes called the Q expansion principle. Which says that actually we take integral modular forms of weight K. They're the same as global sections. So this denoting global sections. And this is the moduli stack for elliptic curves. So here we had only considered complex elliptic curves, but there's a notion of elliptic curve over any commutative ring. And you can build some modular stack of this. It's not so important what this is exactly for this talk, but some object which upon complexification becomes this thing. And there you also have this sheaf here. And there are kind of several ingredients here which are not so easy, maybe. And one tricky point I just want to mention on the side is here I had holomorphic functions. And a priori, these sections I have of this line bundle will be also holomorphic sections. But here I'm suddenly in the world of algebraic geometry, so somehow I need a mechanism to force my holomorphic functions to be algebraic functions. Luckily, there is this theorem, and it works. And yeah. And then there's also this more ad hoc integrality condition, really conceptually the same as having this integral moduli stack of elliptic curves. Questions so far? Yes. Okay. Some chalk. Okay. So there was not so much topology as of now. Only some slapstick and some modular forms. So I want to say a little bit about TMF. I know that if you have not seen any of this, you won't understand all the words, but I hope you still get some picture. So okay, so TMF is an E-infinity ring spectrum. Okay. We said that modular forms are sections on the of some line bundle on the moduli stack of elliptic curves. So better should kind of have a version of this kind of line bundles which live in a world of spectra instead of abelian groups and whatever. So we have some higher algebraic version of this. This is exactly what's happening. So this is Gauss, Hopkins, and Miller exists a sheaf traditionally denoted O top, E infinity ring spectra. This. And we define team F as the global sections. O top. Okay. So you might not directly understand what it means to have a sheaf of E infinity ring spectra on some stack, and there, if one wants to give the detail, one could give a whole lecture about what this actually means. But yeah, maybe you get the picture. That we now have a higher algebraic version of this, but there was like a lower algebraic version. And this, I should say, this sheaf has a property, namely we can compute its homotopy groups. And they're exactly, so it's 0 if t is odd, which is maybe not so interesting, but it's omega to correct power, and it is t half if t is even. So we see all the things we had to take sections of to get modular forms, we see back in this one sheaf of spectra. Let me not erase this, because this is actually important. So it turns out there's an associated spectral sequence called the descent spectral sequence, which, so a priori this goes, so the E2 page is a certain cohomology group, and this goes to a homotopy groups of TMF because it's a global section, so it's completely general if you have some sheaf of spectra on something. But then you observe that this thing here was actually, well, I just wrote it down. It's this sheaf's omega, or something completely algebraic. And so if you have a spectral sequence, there's an edge homomorphism. So there's an edge homomorphism from pi t of TMF. Well, it goes to H0 of ML pi t O top. But well, this is exactly, well, it's 0 if t is odd, and it was H0 of ML omega to the t half if t is even. And this is the same as MF, this ring of modular forms. So this is exactly this phi I had at the very beginning. So you get an edge homomorphism of a certain spectral sequence, and now you see why it has in general no right to be either injective or surjective. Because this spectral sequence is, unless you rationalize, highly non-trivial. And so you imagine like the spectral sequence, well, if it looks like this, the upper half plane spectral sequence. I mean, I was postdoc of Mike, but still I haven't learned. This is my spectral sequence skills. Well, here's eta. Okay, so why is it not injective? Because, well, if you have the edge homomorphism, you forget about all the higher cohomology groups. So everything, you forget about everything in the spectral sequence which is above the 0 line. For example, this little eta here. Little poor eta was forgotten by this homomorphism, and so it's in the kernel. And everything which survives above here will be killed by this homomorphism. And then why it's not surjective? Well, an edge homomorphism is not surjective if there are differentials which go on from the 0 line, and well, there are. and just draw it schematically. There are some differentials like this, the sources of this non-trivial differentials won't be in the image of the edge homomorphism. For example, this delta will be the source of a differential. Any questions about this general introduction to TMAP? So Mike understood everything, so it should be fine.
This is why I don't say that.
Okay. So now, okay, I gave some kind of this kind of complex analytic story, this kind of more algebra geometric story, and so on. And now I want to switch gears. I have a completely empty board for that, and tell you why. Tell you one reason why beyond homotopy theory or chromatic homotopy theory and whatnot, topological modular forms are important. Just check whether I forgot to say something. I think it's good. Topological modular forms and quantum field theories. So this story I want to tell goes back to work of a lot of people, in particular Witten, Siegel, Stolz, and Teichner. In case you're allergic to physics, please move to the back. But it will, because as I said, we're late in the afternoon, we'll keep it light on the physics. So there's some mysterious thing in the middle, which is called quantum field theories. Can one read green on green?
And on the green.
Sorry, I didn't want to ask for a general statement or a specific one, but I clearly didn't learn my lesson during my PhD. So we have quantum field theories, and there should be a lot of adjectives, and I will add one later. These are two-dimensional quantum field theories, and I don't expect you to know what this means because at least mathematically nobody knows what this means, as far as I know. So you don't have to either. So I want to get a black box, or I draw it in green because green is the color of hope. So we might hope some theory like this exists. I stole this joke from Stefan Stolz. Okay. Okay. And so also in green, there's a map from here to the homotopy groups of TMF. And because I need to put a number here, I should also put a number here. And I just write with anomaly. Okay, whatever this means.
But you could use white for IKTMF, right?
Oh yes, sorry. And I should, because we know what TMF is. So I messed up my convention. Okay, thank you. And then I can go further to okay. So this is not only green, this is also dashed, because this is not really established on any level of rigor. Even like physically, like physics, not even physics level of rigor, it's like a conjecture, maybe that's something like this should exist. While the composite is something which is known on the physics level of rigor, at least, it's called a partition function, whatever it is. Okay, so why I'm telling you this is an ill-defined notion which has something to do with this. I'm not telling you to convince you that it has some TMF has some application to physics, although I think it can say something about this, but that's not the point here. Just want to say that it can actually, this thing can inspire some mathematical constructions, although we don't quite know what this is. So for example, so say you start with a string manifold. O M of dimension k. Okay. So people don't know what a string manifold is, at least for our purposes, means, so if you have a manifold, we have the tangent bundle, which is classified by map to BO. Then we can take the 8th stage of the white et al, so we kill the lower homotopy groups, and then we want to have a lift in this diagram. So, and I mean, if I were to 4 instead of an 8, it would be called a spin structure, and then, well, to have a fancy name, one calls it a string structure. Okay, and has been on the physics level of rigor, so it's a non-dash green arrow. It has been long now how to associate to this the quantum field theory since the 80s. So, if you compose these two arrows, you must be able to associate to a string manifold an element in the homotopy groups of TMF. And what was first done by Witten, who, as you probably know, is a physicist, he constructed a rigorous version of this arrow, which is called the Witten genus. It's also still from the 80s, I guess, just inventing a year, 87. And then, a while later, Endo, Hopkins, and Resk managed to construct this arrow, and actually they constructed something much better. There's the Thom spectrum for string manifolds, so string cobordism. They construct a map of E-infinity ring spectra from M string to TMF, which realizes this. But I think it's very fair to say that this physics idea was first from Witten, and then later it was realized mathematically. Although I think, I'm not sure in this paper in Hopkins West they actually mention any quantum field theories, and of course in the construction there won't be any. Okay, and there's actually another thing one can do. One can look at quadratic form. So positive definite, not strictly necessary, but only necessary for some parts I want to say, positive definite quadratic form. Q, or bilinear form, B, which is unimodular. So there is, again, on the physics level, a construction like this called a lattice conformal field theory. And so if you look at this diagram, there should be a way to go here. And well, to here, we can easily go. This is a theta function we considered earlier. Only that, depending maybe whom you ask, but actually one should normalize it slightly differently. One should divide by, I didn't say it's, sorry, from z to the d to z. It's, we have to divide by a certain power of delta, which is not so bad because delta is invertible. And actually, it's also not so bad because you can show d it must be divisible by 8 under this circumstance. But maybe you can ignore this for a moment. And so, this picture says that we should also, so it's not quite clear whether it's green or white, because it's like constructing such a thing would be a precise mathematical thing, but it's motivated maybe by physics. There should be such a thing here. And k is, k should be minus d1 half, minus d half. Okay, so it's not just some abstract statement that one should, that somehow this theta function lifts to TMF, or this kind of renormalized one, but there should be, in some sense, one from this picture, one expect that somehow happens canonically. And So I didn't say any theorem. It's a bit mean that there's a slight slope here, but maybe I'll learn at some point. Good that I have 2 talks. Okay, because I didn't state any theorems I was involved in so far, it was no need to mention any collaborators. But actually, I'm part of this project I'm talking about is together with Slava Krushkal, Sergei Gukov, and Dupay. The last 2 of these actually have a physics background, and actually I've learned a lot about TMF from them in the sense that because they have a lot of physics intuition, they have to make some prediction about TMF, which I would otherwise not have come up with. So somehow I've learned that this can be a useful picture even the case that maybe you have no interest in quantum field theories, but only want to learn more about TMF. And if you have some interest in quantum field theories, maybe this is a bonus. Okay. Apparently, no questions, or are there any questions? Why there's the minus? Because I divided by, hopefully I did, or it's like minus d. No, I have to calculate. So if I have 12, I think it's minus d, because before it was d half, and now I divided by 12 times d divided by 8. So it's 3 half times d I have to subtract, so it must be minus d. Thanks.
How are you supposed to think of these QFTs with anomaly?
How do you think about QFTs without anomaly?
I don't.
So it's a thing that, so one thing is usually maybe you want to have some, okay, QFTs might be some magic, but at some point you want to have some concrete things out of this. Maybe you get some function out of this from a QFT. You want some partition function, whatever. You can plug in points and you get numbers. Okay. But if you're an anomaly, it doesn't quite work like this. You might only get not a function, but you get a section of a line bundle. And then, well, I mean, then you can still try to work with this. Maybe locally you can trivialize it, whatever, get numbers of this. But you can replace functions by sections of line bundles. This is essentially what happens. Further questions? Okay, then, let me reformulate my goal, and because I said we don't really want to answer that question at the beginning because Hopkins already did. I might pose a more general and slightly modified goal. The goal define for every symmetric bilinear form B a class pi star TMF such that I'm not sure, give a name such that the image in modular forms is this theta function of Q if B comes from a positive definite. Quadratic form Q. So to appreciate this, I must say there are kind of 2 generalizations happening here. First of all, I said B doesn't need to be positive definite anymore. It can be more general. And second of all, it doesn't necessarily have to come from quadratic form. So just as a small reminder about the relationship between quadratic forms and bilinear forms. So there's an injection from quadratic forms into the symmetric integral bilinear forms. The set you send Q to VW goes to this polarization formula sort of thing. But not everything is in the image. The reason is, if you want to go from a bilinear form to a quadratic form, you might say, oh, I just send V to B, sorry, yes, no one can see there, to B of V comma V, but you will realize that this is not inverse to the formula, other formula. You have to put a 1/2 here. And it happens that this is not always an integral quadratic form. And the condition that it's integral is exactly that these numbers are even. So quadratic forms are exactly what's called the even bilinear form. So this sense is more general. Okay. So this is the goal I want to pose, and I will, to a certain degree, answer next time. But there are some challenges related to this. So as I said, I have a limited tolerance for formulas, but the theta function was just defined by formula. And there's something somehow it's hard to deal with in our area. You just write down some formula and hope that you can realize it by some object in spectral algebraic geometry. And so you need something which is more canonical. But in some sense, this theta function, I don't know a direct way to write as something more canonical. But there's some variant of a theta function, a multivariable theta function, which is much more canonical. And so it's often good to avoid early information loss and only pass through the information loss at the last step. Have something with more information is more canonical, and only at the very end you drop the information you don't want. So let me say.
You want to assume unimodularity now? Or
oh yes, sorry. So something one can say without, but then it won't be in TMF. Okay. So let me, to guide the further way, tell you what this multivariable theta function is. Or maybe what I wanted to say. So, okay, before I tell you what the multivariable theta function is, I want to say the theta function were modular forms. So this multivariable theta function must be something more general or bigger or something like this. And this more general or bigger thing are called Jacobi forms. So we'll come to the last part, which is, I guess, part 4. Jacobi forms. While modular forms has been known since the beginnings of time, Jacobi forms are a bit more recent. So these are due to Eichler. So there's a book by Eichler and Zagier, which, if you have some tolerance for formulas, it's a very nice book. I guess it's from around 1990 or something like this. The theta functions themselves, which form important examples of these, are much older. They are due to Jacobi and Riemann and so on. Okay. Let's see what I want to say. So, definition of a Jacobi form. And I will only give a very rough definition. So, let B be a symmetric bilinear form. And I only will consider integral ones, not go over C or whatever. So, Jacobi form. Maybe I should say. Let me write it. the Jacobi form of weight K and index B is now a holomorphic function. Doesn't go from the upper half plane only to the complex numbers, but I have d extra variables satisfying some transformation behavior dependent on K and B and a little bit extras. Okay, so well, I mean it's a bit. I should say, okay, I must say I cannot myself remember this exact transformation behavior. It's a little bit complicated, but I should say with respect to which group, with respect to the action of SL2Z times Z to the 2D. So what is the action? So SL2Z still acts on H, and Z squared acts on C, because, well, I can standard embedding of Z squared into C, and then I do this D times. So some of you might have seen elliptic functions at some point in their life.
What's the action of SL2Z on Z to the 2D from the zero product?
I act on each Z squared, and then a diagonal line. So in some sense, one can say, which might be more transferring in a few moments, that this is a mixture between modular forms and elliptic functions. And the important example for us are, so if Q is positive definite and unimodular, I can do the following. I can write down F tau Z to be the sum over V and Z to the D of Q to the V with E2 pi I B. So the details are not so important, but one thing which might be important is that I can recover the classical theta function if I just peg Z equals 0. So theta Q, sorry, didn't want to call it F, I want to call it capital theta Q. Theta Q is just so I plug in 0 here for Z, this term becomes 0, so e to this becomes 1, so I just have the old guy. So why is this any progress? So good news is this is a bit more canonical everything. So let's say we look at Jacobi forms of weight K and index B, and I put a C here because now everything is complex and holomorphic, whatever. It's free over modular forms. Sorry, let's put a star here. Of rank 1 on the theta function. So in some sense, I don't have to know the definition of the theta function. If I know the definition of Jacobi forms, I can recover the theta function. I must say I'm hiding a little bit under the rug here. I maybe comment about this in a few moments. Okay, so this is now much more canonical in a sense. And then I can recover this classical theta function by plugging in 0. And The rough plan, I will say much more about on Thursday, is define for every B topological Jacobi forms. TJFB. And then show that for B unimodular, TJFB is equivalent to TMF up to some shift. Then I have a generator here in the corresponding degree, and moreover, there will be, like plugging in 0, there will be a morphism like this, and then this generator will go to some element in pi star of TMF. So this will be a strategy we have. And I can already foreshadow, because I mean there must be something equivariant in this whole thing. This will be some twisted form of equivariant TMF actually. And this will be the way one tries to build this. And actually one builds it. Okay. So my time is nearing the end. Are there any questions on this? So, yes.
You define those Jacobi forms for every bilinear form B, and you say it's free of rank 1 over the theta functions for quadratic forms. But over there you said that these are not like isomorphic, but you don't have an inverse. So it seems like something is missing if B does not come from a quadratic form.
Yeah, so some of the point is that if I work algebraically or holomorphically or whatever, the whole thing only works well if we have positive definite, and ideally that it really comes from a quadratic form and not just a bilinear form. But if we work derived, then everything works for every bilinear form. You have these kind of annoying things, for example, that, I mean, for example, if you kind of think about this kind of picture, if you have anything which comes from a higher cohomology class, you don't see on the modular form level, but you see on the TMF level. This kind of stuff. Yeah. Yes.
What kind of homotopy groups do you get with these maps?
I mean, this is, as I said, it's work in progress, but I'm pretty sure we can get eta and nu, and conjecturally we get all the theta functions, but there's like there's one slight caveat in this, which I will mention at some point, probably next time. Yes, and we don't know in general what we get, but these are some things we get. For pretty simple guys, like nu would be associated to quadratic form x squared. One of my favorites. Are there more questions? Yes.
I mean, I don't even know if that's an interesting question, maybe, but is there an interesting modular space of bilinear forms which now acts on this?
I don't know. In some sense, well, there will be some answer. I mean, it depends for which purpose. It might be different purposes, it might be different modular spaces. But actually, how bilinear forms in some sense will come up next time, and I'm foreshadowing again. Turns out that this is the same as bilinear forms. maybe not obvious, but isomorphic, these things. And, well, okay, just delete the pi 0 and then you have space.
How much PM?
P4 is the fourth Postnikov truncation. Actually, because I have only a little bit of time left, I can explain something about the isomorphism. You can use it as input next time. Because it's actually quite cute. So how does P4 BO look like? Well, the homotopy groups BO satisfies broad periodicity, but we don't have very far because we're only interested in low small homotopy groups. So we have a Z mod 2 to write a little bit bigger F here. I have a Z mod 2 in degree 1, a Z mod 2 in degree 2, and a Z in degree 4. Because this is simply connected, this one we can ignore. And let's just concentrate first on the upper one. So say we look at instead only into the KZ4. These homotopy classes are known as a fourth cohomology, and this is also known as CP infinity to the D. So we all know what the fourth cohomology of CP infinity to the D is, hopefully. Namely, the cohomology ring of CP infinity to the D are all polynomials in D variables. We look at the fourth cohomology, we look at quadratic polynomials. So these are quadratic forms. So clearly you have a map from here to here, from the inclusion of KZ4, the map from KZ4 to the fourth Postnikov truncation. And well, it turns out that this is exactly this map. That is extra Z mod 2 exactly is somehow controlling this co-kernel. And in some sense, the bilinear forms, the relevance comes from this thing, and it happens to be bilinear forms. I mean, this, yeah, I'm not sure. I mean, this must have been very classical. I didn't find it anywhere. Maybe somebody can enlighten me. So, more questions.
Can you re-explain what you meant here? It's TMF, square brackets, question mark, near the generator going to element.
Yes. So let's give this question mark. Let's call it, I'm not sure, what's a good letter? M. So this is an M-fold shift, so M-fold suspension of TMF. And because I have an element, as an element 1 in pi 0 of TMF, and this corresponds to a certain generator of pi m of TMFM, M-fold shift. That's just suspension isomorphism. And this generator is then sent by this composite to an element in pi m of TMF. So this is what I meant.
Thank you.
More questions?
So what kind of gizmo is TJF a TMF module spectrum, or?
I mean, it will be a, yeah, it's a TMF module spectrum. But we'll say more about this next time.
Okay, so it wasn't really clear when the talk ended, but it's now. Usually we would now have an opportunity for questions. We could just thank Lennart again because we only had 5 minutes for questions. And 2 more announcements, or let's thank him again after the announcement. So the first announcement, in their great wisdom, the organizers decided to have a talk at an unusually early time tomorrow morning, shortly before dawn, 9:15. So make sure you're here an hour earlier. It's only tomorrow, don't worry. So it's going to be fine again on Thursday and Friday. The other thing is we're going to have a question and answer session right after this, but I do suggest we have like a 5-minute break, and then whoever's interested comes back. And we thank Lennart again for the nice talk.